EC 201, lecture 27. Yesterday we were looking at the active load, where the basic idea was to notice that when you want to get larger and larger gain with a traditional common source amplifier, the gain is of the form minus GMRL, and if you want to keep the GM of the transistor the same but to go on increasing the gain, you have to go on increasing RL, and then you found that the only way you can keep the transistor in saturation is to make the power supply voltage larger and larger and larger. Then we decided that this is not really working for us, and then made the observation that instead of having the resistor, if we put then in its place a nonlinear element whose incremental resistance is very large but whose characteristic is kind of offset towards the left with respect to a large resistor, then we will be able to get a much larger gain even though the supply voltage was very small. So that's how we came up with the active load, where this is I1, this is W by L, so is this, and this is VD. And if I plotted VD on the x-axis and ID on the y-axis, the PMOS characteristic would look like this, and this being VDD, this is I1, and this curve, this corresponds to VG is equal to VA. And when you have an NMOS transistor as the load, what is the characteristic of this chap here? It will be something like this, alright, and this assumes that the NMOS transistor has got some finite lambda. If the lambda was 0, then in this portion the I versus V characteristic would be perfectly flat and parallel to the x-axis. So let's spend a couple of minutes and figure out what not the small signal gain would be, but what the input versus output characteristic would be. In other words, let us try and plot VD versus VG. There is the input terminal, there is the output terminal. I go on varying VG from say 0 to VDD, and I would like to find what the output voltage does. So when VG is 0, what do you think happens? How will I use the graphical technique to figure out what happens when VG is 0? So can I use this graph as is to find the output? What should I do to find the quiescent output voltage VD when the applied VG is 0? What does this curve correspond to? VG is equal to VA. Is that what we are looking for? No. So what do you have to do? You have to draw the corresponding curve for VG is equal to 0. So where will that curve lie? How will that curve look like? Up or down? VG is equal to 0 corresponds to a VSG, which is very, very large and equal to VDD. So that curve will be way up. This curve is not what we are looking for. We want the curve for VG equal to 0, and that will look probably like this. Is this correct? First of all, it will have a larger triode region. Why will it have a larger triode region? VSG is very, very large. Okay, will it have a saturation region at all? Yes, no, maybe? Yes, okay. So is this curve correct? The saturation region will definitely exist, so you must have some portion of the curve which is completely saturated, and then a large triode region corresponding to a large VSG. What is the output voltage graphically? It is the intersection of the red curve with the black one. If a VG is 0, the transistor, the PMOS transistor is operating in which region? It's operating in the triode region, and the quiescent voltage at the drain of the transistors is close to VDD. When VG is 0, let's say this is VDD, the output voltage will not quite be VDD, but it will be somewhere there. Is that clear? Okay. Now let me start increasing Vg slowly. So what do you think will happen? For every Vg, I need to plot a curve like this, find the corresponding point of intersection and then plot the output. Correct? So if I increase Vg slightly, what do you think will happen? The corresponding curve will be something like this. It will have a smaller saturation current as well as a smaller area in the triode region, and you can see clearly that as you go on increasing Vg, the potential at the node, at the drain of the PMOS transistor will keep falling. So eventually you will come to a situation where the Vg is such that the saturated current of the PMOS transistor is exactly equal to I1. I go on increasing Vg in this fashion, these curves will go on falling. Eventually I will find that for a certain particular value of Vg, the PMOS transistor is in saturation and so is the NMOS transistor. And what will be the output Vd? Can you relate it to VDD? It will be roughly equal to, it will be roughly in the middle. You understand? Does it make sense? Okay, so as I go on increasing Vg, the curves that I need to plot will have larger and larger regions in saturation. So eventually I will always come up with some particular value of Vg where both the transistors are in saturation, in which case the point of intersection will move from here to, originally it was here, okay. Then if I change Vg by an infinitesimally small amount, the current will basically do this. So the point of intersection will move here. Then if I change Vg by an infinitesimally small amount, you can see that the point moves here. For the same incremental change in Vg, can you comment on the rate at which this point of intersection moves along this line earlier versus now, when the Vg is approximately equal to Va? Do you understand the question? Originally Vg was 0, we had this set of curves, and at that time we found that the PMOS transistor is basically sitting in the triode region, and as I increase Vg, the output voltage certainly decreases. But the moment I come to a situation where both the transistors are in saturation, even a small change in the Vg will result in a large change in the point of intersection. What does that mean physically? It means that the gain is very, very large in that region where both are in saturation. And if I increase Vg, so that basically means that if I continue to draw this curve, so initially the rate at which Vd falls is slow, then the rate of fall is very, very rapid, and beyond this what happens? So if I increase Vg beyond this, what happens? The NMOS transistor will now start going into triode. Alright, and the points of intersection. The output voltage is basically the x-intercept of this point of intersection. So initially the output voltage will change slowly because the PMOS transistor is in saturation. Then it will fall very rapidly because both the transistors are in saturation, then what happens? If Vg is increased beyond this value, you see that the NMOS transistor is in saturation, and even a large change in the Vg corresponding to all these curves results only in a small change in the output voltage. So if I plot the complete characteristic, it will look like, will this go to 0 at all? Yes, no. What happens as I go on increasing Vg, eventually what will happen to the PMOS transistor? So as Vg goes higher and higher and higher, what do you think will happen to the PMOS transistor? How much source gate voltage do you need for the PMOS transistor to conduct? You need Vt. So the moment the Vg goes to VDD minus mod Vtp, the PMOS transistor will get cut off. So if the PMOS transistor is cut off, what happens to the current? The current is 0. So what will happen to the output voltage? It will also be 0. If the PMOS current is 0, the PMOS being 0 will correspond to I being 0. That will intersect the NMOS characteristic at 0. So the output voltage will be 0. This is VDD. This is Vg on the x-axis. This is VDD. And what is this voltage? VDD minus mod VTP. Oh, VTP. Okay, for the purpose of this class, I just assume that VTP is positive. So this is the region in which the gain is very, very high. And if the lambdas of the devices tend to 0, what can you comment? Can you make any comment on the slope of that region? It will become higher and higher, and eventually it will become infinity. Okay, so this is for non-zero lambda. If you had in a 0 lambda, you will end up with something like this. So this corresponds to lambda p and lambda n being equal to 0. Okay, where the slope here, it's a vertical cliff. Physically you can understand it by looking at the slopes of these two curves. If this was exact, if the red curve was flat, then what happens? Even a small change in the gate, applied gate voltage will shift this curve up and down by even a small shift of the PMOS characteristic up and down will cause the point of intersection to abruptly shift from the rightmost side to the left side. Does it make sense? Yesterday you saw that the incremental gain is given by GMP times RP parallel Rn. Alright? And if the lambda becomes 0, RP and Rn both tend to infinity, which means that the incremental gain becomes infinite, which will cause the slope of the characteristic to be infinite. Alright? So, does this characteristic remind you of something? When the input is low, the output is high. When the input is high, the output is low. The inverter. Find all input voltages less than a certain something to be your logical 0, and all input voltages greater than a certain voltage as a logical 1, then this defines a digital gate. This is a NOT gate or the inverter. You understand? The digital guys are terribly excited by the flat portions of the curve. As far as analog designers are concerned, the flat portions are totally useless, okay, because they can't give you any gain. What we want is the slopy region. Digital guys get very nervous if things start operating in no man's land. Rule of life, which is any inverting amplifier can be operated as a NOT gate. You understand? Because you know that if you have an inverting amplifier, the characteristic output versus input must look like this. And you know that in real life, nothing extends all the way from minus infinity to plus infinity. It must, stop somewhere there and must stop somewhere here. So, whenever you have an analog inverting amplifier, it must follow that if the input voltage excitation is sufficiently large enough, you will be able to operate it as an inverter. Okay? So, the vice versa, the reverse thing is also true. If you gave me a digital logic gate, a NOT gate, I will be able to use it as an inverting amplifier. So next time when you come to the lab, you will see this happen. We will take an IC which has got 6 NOT gates in it, which are all CMOS inverters. This is this is a chip which is commonly used by a lot of digital folks. Okay, it's got 6 NOT gates on it. Okay, and a CMOS inverter is an inverting a NOT gate is as digital as anything can get. We will take that IC and make with it a filter and amplifiers and so on, which are as analog as things can get. So there's no circuit in the world which is a digital circuit or an analog circuit. It is the way you operate that changes the nature of operation of the circuit. You understand? Another aspect that I wish to point out is the following. The incremental gain of this amplifier will be large only when both the transistors are operating in saturation. One obvious question is, how will you ensure that the two operate in saturation? All that we are doing is applying some gate voltage here and some gate voltage here. And you see from the characteristics, from these characteristics you see that, especially when the lambda is very small, you see that the slope of the input versus output characteristic is very, very sharp. In principle it is infinite. Even if there is a small error in the biasing voltage Vg, or a small error in I1, what do you think will happen? So if the NMOS transistor, if the PMOS device and the NMOS device, both of these are biased by independent voltages. So if this is operating in saturation, this current is exactly equal to I1. If this is operating in saturation, this current being drawn is exactly also equal to I1. And this potential is somewhere between VDD and ground. Even if there is a small error in I1, either because this gate potential was slightly larger or smaller, okay, or this gate potential was slightly larger or smaller, what do you expect to happen to the potential of this node? These are two independent current sources. One of them is slightly larger than the other. So into this node, there will be a net current flowing, which will cause the potential of this node to go on rising because of the difference in currents being pushed into the node and being pulled out of the node. So this potential will go up and up and up eventually until what happens as this potential keeps going up? The PMOS device is being pushed towards the triode region. So initially when both of them are in saturation and there's a mismatch in the currents, the node potential will start going up. As it goes higher and higher and higher, it will cause the PMOS transistor to get into the triode region, and once it gets into the triode region, the current will drop and the output voltage will settle exactly at that point where the current of the PMOS device in triode is equal to I1. Okay? So when you have a very high gain amplifier like this, you will get the high gain only when you are biased in precisely this small window. Even a small change in the input bias voltage will cause you to be either operating in this region or in this region. Does that make sense? And this is fundamentally true for all high gain characteristics. It's nothing special with the MOSFET or whatever this is. If you have a nonlinear characteristic of this nature, where the incremental gain is very high in a small region, then you must be very, very careful in fixing your quiescent operating point. Alright? And then, one of you may ask, so what is the big deal? I mean, if in practice it's probably not possible to pick the operating point we said, we've always been saying we'll put a battery here and battery there, right? And make sure that this, the operating point is correct. In practice, there will be errors. So, the moral of the story is, all these high gain amplifiers, where do you think we will operate them? We've used it in a negative feedback loop to make the input-output characteristics of the feedback system to be independent of the properties of the forward amplifier. So, all these high gain amplifiers should never be operated open loop, okay? They will always be operated in, the feedback loop will force the amplifier to be operating in this region. So, please remember this as a general rule. A high gain amplifier can never be operated open loop, because even a small change in the operating point will cause the output to saturate. Active load case. If I assume that both the transistors were in saturation and lambdas were 0, Vg is chosen such that this is equal to I1 and this is also equal to I1. So, the incremental equivalent of the PMOS transistor will simply be some Gm times Vi. Okay, this is Vd plus Vout. Okay, what is the incremental equivalent of this chap? It's an open circuit. Yesterday we saw that this was Rp and Rn. If Rp and Rn both tend to infinity, this simply becomes an open circuit. Okay, which makes sense, because what is the incremental gain now from input to output? The gain is minus infinity. Rp, Rn both tend to infinity, so Rp parallel Rn will tend to infinity. Gm times Rp parallel Rn will therefore tend to infinity, so the gain is minus infinity. Many circuits can give you the same incremental equivalent. So, let's try and see if it's possible to generate from this circuit. We've come to this incremental equivalent. Now, let's try and see if it's possible to generate other circuits which have the same incremental equivalent. The cheapest thing you can do. You don't have to think at all. You just look at the circuit diagram, you'll be able to tell me. You can change the NMOS and PMOS. Have an NMOS transistor in the giving gain. The load can be a PMOS current mirror, and you change the appropriate directions of current and all this other stuff. So let me show you another alternative. I can simply redraw this as Vi, Gm1 times Vi. This is ground, and this is Gm2 times Vi. This is ground, and I will connect these together. These two together, and obviously the grounds are the same. When will this chap be equivalent to this guy? All that I have done is split this controlled current source Gm into two parts, one which is Gm1 and one which is Gm2. So the two will be exactly identical and indistinguishable from each other when Gm1 plus Gm2 is equal to Gm. Does that make sense? Okay, great. Now let's see what happens. So this can be identified with a transistor, alright, operating in saturation. So I will identify this with an NMOS transistor. This can also be identified by a transistor operating in saturation, and we know that whether you have an NMOS transistor in saturation or a PMOS transistor in saturation, they have the same incremental equivalent. I say, hey, why should I be partial to NMOS all the time? I will identify this guy with a PMOS transistor operating in saturation. So I have a PMOS transistor, so what should I do to the source, the drain and the gate? I should connect it to the gate of the NMOS transistor. Okay. What should happen to the source? Source should be incrementally grounded. Okay. What happened to the drain? The drain should be connected to the drain of the NMOS transistor. Does it make sense? When you replace every transistor with its incremental equivalent circuit, it will have this equivalent. This circuit for incremental signals. Can you suggest the real circuit? How would you expect quiescent current to flow in the PMOS transistor? I mean, can the PMOS transistor be source be connected to ground? Real ground? No, it has to be connected to incremental ground, and we know that the quiescent current of the PMOS transistor has to flow this way, and the quiescent current of the NMOS transistor to flow which way? The same direction. So that's great, because then you can connect them in this fashion. Okay, so this is connected to VDD. Obviously, when you draw this, we have to find the right bias voltage, which will make sure that both the transistors are in the saturation region. Let me call this W by L of the PMOS device. This is W by L of the NMOS device. Can you help me figure out what VG must be to ensure that both of them operate in saturation? How will I find out? We started off with this guy, alright, and then we said I can split this up as two voltage controlled current sources operating in parallel. And then I said I can identify one with an NMOS and one with a PMOS transistor. Okay. And that leads us to, this is how the two transistors must be connected as far as the incremental signals go. And then we realize that the quiescent current in the PMOS transistor flows from source to drain, and the quiescent current of the NMOS transistor flows from the drain to the source. So it seems quite nice that you can stack them on top of each other, and they should be happy as long as the proper bias is applied to the gates. The question now is, what is the gate voltage I must apply such that both these transistors will be in saturation and the drain currents will be the same? I know that this current, the drain current of the PMOS transistor, is the same as the drain current of the NMOS transistor. I know that I want to make them both operate in saturation, which basically means that 1/2 mu P COX W by L of the PMOS device times VDD minus VG minus VTP the whole square must be the same as 1/2 mu N COX W by L of the NMOS transistor times VG minus VTN. So solving this equation, you will be able to get the value of VG you need to apply. Transistors are in saturation. If you now apply a small signal around this quiescent VG, then what do you expect for the incremental gain? If both of them are operating in saturation, what did we say that the incremental circuit will look like? Find the incremental equivalent of this chap here. If the lambdas of the devices are 0, then it will be the GMN plus GMP and flowing through an open circuit, so the incremental gain will be infinite. So this is the famous CMOS inverter, and the symbol for the CMOS inverter is, so this is denoted by this logical symbol which you have seen. If I plot V in versus V out. When V in is very small, close to 0, what do you expect the output voltage to be? Close to VDD or exactly VDD? V in is 0. What do you expect the NMOS transistor, in what region of operation do you expect the NMOS transistor to be? It is cut off. Okay, so when Vn is less than Vt, less than Vtn, okay, the NMOS transistor is cut off. Alright, so the NMOS transistor is cut off, the drain current is 0, and what region of operation do you expect the PMOS transistor to be in? What is the drain current with the PMOS transistor? The NMOS transistor is cut off, so basically it's like not having a transistor at all. This is what it is. Okay? So is that PMOS transistor cut off or is it conducting? What is the definition for cut off? The transistor is cut off when VSG is less than VT. So do you think VSG is less than VT or greater than VT? Greater than VT. So the transistor is certainly not cut off. Okay. So, but the drain current is 0. That means what? It's operating in the triode region. Alright. The transistor wants to give current, but there is no path for the current to flow. And under this circumstance, the output voltage is simply 0. The VDS of the transistor must be 0, which means that the output voltage has to be VDD. In other words, if you took a PMOS transistor and plotted its characteristics, this is VSD, this is ID. Okay? The only place where ID is 0 is when VSD is 0. VS is VDD. VSD equal to 0 means that the drain must also be equal to VDD. Does it make sense? So by the same token, if the input voltage exceeded VDD minus VTP, okay, what do you think will happen? So we have finished this region. We are now trying to attack this region. What happens now? The PMOS is cut off, okay, and now the circuit looks like this. Now the NMOS transistor is operating in N is in triode and the P is off. What will be the output voltage? 0. And somewhere in the middle, this is where we had that VG. Okay, where both of them are in saturation. Okay, where there the characteristic must have an infinite slope, so it will be very sharp like this. So this is that thin line where both N and P are in saturation. So as you keep applying the input voltage, N was off, and here N is in, here N is off, here N is in saturation. So if I was to go from off to saturation, what must it, the N must be in, please note, N is off originally. What is the VDS across the transistor? The VDS across the transistor, across the NMOS transistor is very large. It's equal to VDD. Okay? As the input voltage becomes larger than VTN, what happens? The the NMOS will be in saturation because it's got a VGS is greater than VT, okay, just greater than VT for example here, alright, and the VDS is very very large. So the NMOS transistor is in saturation. P will continue to be in the triode region. And then what happens here? In this region, N will be in triode, P will be in saturation, and then as we saw, P will be off and N will be in triode. You only get the high gain when both of them are in